Okay, we talked about the monopole and its properties a little bit in the last lecture. Today I want to start here, briefly remind us of what it does. But dipole, quadrupole, all of the multiple fields are really beautiful. It's worth seeing that, and this is something that connects to the three-dimensional analysis of multiple functions, which we won't do in this class, but we will do in any other classes that involve symmetry analysis. The first start here is the dipole, and I'm going to do that in a minute. I've got this lecture starting on about page 30 of the programming of the whatever you want to call these lectures. The thing that is important for today is I want you to get ready for complex analysis of resonance, and that is in Unit 4, and the functions that we're using, particularly the dipole function, plays a major role in that analysis, which I'll show today as we go through these various multiple functions. And also today I want to talk about the series. We started this lecture with the analysis of how good a power series was for approximating sine and cosine, and then that led to the understanding of complex functions. The thing that we'll do today, if we get time, is the Laurent and Maclaurin, or whatever you want. The names are sort of up for grabs, but in particular the Laurent series includes not just positive powers of the independent variable z, but negative powers as well. And those things are multiple functions, which we're about to discuss here. So basic idea of this, and I'm going to go ahead and jump ahead to that page right here, but I want to clear that screen so we can actually look at this function being produced. And this is what we call a physical dipole. It has a finite distance, del, between something with a positive charge, if you were thinking of a positive current, if you were thinking of that, but in this case I'm thinking charge, and then that's what we would call a pole, and then there's a hole, which is just a negative pole. Those two put next to each other makes a potential surface like that, and I'd like to very quickly construct that and look at some of the geometry that just sort of falls out from building that function. And then what we'll do is we'll let that finite del shrink to an infinitesimal del, and what you'll see is that these dipole functions are obtained by a derivative. So the whole idea of a complex derivative giving us from a monopole, taking the derivative of it, gives me a mathematical dipole, a field that we'll look at in some detail here. So let me switch over. Unfortunately, even though the internet system for the university is completely hosed at this moment, we've got all this. This is an old program that sits right on the old computer, so we can do this fairly easily. And what I've done here is I've picked out of this menu the physical dipole that we'll look at first, and I'm going to go ahead and let it plot out the scalar potential and the vector potential. Let's go ahead and plot the field here, and then I've got it set to do the scalar potential. And this is really, I think, quite surprising. This is not something that happens with point charges. But remember, this is a two-dimensional analysis, and what we're thinking about here is the equal potentials that occur for a line charge coming out of the screen. In other words, there are two dimensions where things are varying, but then those two dimensions are copied at every level of this. So out of the screen, in the screen, it always looks like this. So we're making cylinders of equipotentials, really, and this is just cross-section. But what's interesting is that these equipotentials that we're getting drawn here, and it's just doing it numerically, it doesn't have a formula or anything to follow, these are circles. And that's something you might not have noticed by looking at the drawings quickly, but every one of these curves is a perfect circle around some point. They all have different centers, but that is, I think, quite remarkable, and it's going to make a very beautiful coordinate system when we put the streamlines down on top of these. So I'll put as many of these things here as I can to keep it being reasonable, reasonably smooth level. So that's the equipotentials, and then let's go ahead and stop right here and go ahead and do the flux lines, the flow lines, if you will, and it's kind of neat to see those as well. And what you're going to be getting is, once again, circles. All of these lines make circles. And we're making a very strange coordinate system here, which I hope we make use of in some problems later on in the mechanics class, as it advances into the first non-review unit, which is lecture 14 coming up on Wednesday. But you can see pretty easily that these are all just circles that are orthogonal to the other circles. This is called bispherical coordinates. There's some interesting, useful, analytic mechanical solutions, and analytical mechanical solutions are few and far between, unless you have some very special symmetry. You're not going to get that. But this is a picture looking straight down of the major flow lines and equipotentials of this particular 1 over z minus a, and then minus 1 over z plus a, where a is a constant. And we can make this more fancy by making a vortex or something, by putting complex numbers on the charges to make it something really weird. But we've got enough to study just with this. This has got a lot of structure to it, and it's quite pretty. Okay, so this is this is what you get if you look straight down on that thing. And let's go ahead and do that real quickly, just to set the record straight here. So I'm going to go ahead and plot the equipotentials, and I can zoom in a little bit. But you can see pretty clearly what we've got here. All of those curves and the circles are all circled. They're all circular arcs when viewed straight down. But here you can see that we've got a pole and a hole, and they're symmetrically placed. So that's something worth. Let me once again say that if you look at the three-dimensional problem, which is two point charges, you don't get circles. Okay, those are much more complicated curves. This is extremely unusually beautiful and simple. So the other thing, of course, we can
So it's not charged?
say again.
So it's not charged anything? Just
These are when you say charge, what I'm actually plotting here, if it's electrostatics we're doing, is a uniform line charge. That's what the pole is. And this would be the opposite signed line charge, right? I don't know if you remember enough of your electrostatics, but that's what you get
Logarithmic.
with a line.
Yes.
Okay, two lines, one positive and one negative.
Yeah, I'm just trying to like connect to the poles of the Earth,
Yes,
but it doesn't look like.
yes, those,
Does it look similar to the poles of the Earth?
of,
Of what
the North and
distribution?
South Pole?
Is it the same charge distribution?
um,
Because these are along the lines.
yeah, what's not drawn here is a line that this is sitting over.
And then we're only considering the plane
Yeah.
from that 3D distribution of charge.
Yeah, it's a uniform distribution of charges on a line makes this field at all altitudes, right? I mean, that we're plotting the potential here, but that occurs uniformly. In order for this to be an exact description of something, it has to be a uniform thing. Now, you would get a pretty good approximation of this thing by having two charged wires, right? And just stop it here. The field that was felt at the midsection there would be pretty independent of motion until you got close to the end, you see. And that's the way all of this stuff works.
Slice of that.
Yeah, that's right. Yeah, if you sliced in the center and moved it a little bit, it's going to look just like this. You know, it's the idea, of course, of having an infinite line of charge and then negative charges. Fairy tale, but it's the mathematical approximation that's behind this. Yeah. Idealization, we call this, remember? It happens in every piece of physics we know of. Does that answer your
Yes.
question? Yeah. Okay, so the next step then is to do this. Let the thing get closer and closer together. Let this del get smaller and smaller, and you get this is more of an idealization than even what we've got here. But I'm going to go ahead and stop this, and I guess we could really quickly take a look at the flow thing. That's a monster, okay? It's really...
Can you rotate that?
Yeah, it's very, very strange.
Oh,
okay.
wonderful.
Yeah. Now, as I say, TC's making much better graphics out of this thing, so this is one we ought to try out.
And combinations of the two.
Yeah, and of course you can do combination. I was trying that before class, and they were so complicated.
Hard to manage.
Yeah, but
So detailed.
you got to remember that when you put when you turn this around, you're getting the logarithm, the imaginary part of the logarithm, which has this cut. So something's doing this, the same as was happening. Let's go to the slide over there on the third thing. When you put make a vortex out of it by having I over Z, then that supposedly makes a helix that goes forever in both directions. We have that happening here. It's really hard to see that. Okay, let's go ahead, and I'm going to switch over from the physical dipole just to the plain, ordinary, old-fashioned English dipole, which is this guy right here. Okay, and I've got this program so that when you do that, I'm going to erase all of the things that I put in there. So let's do that. And then the dipole for that will be now plotted. Okay, so now the two infinities, the pole and the hole, are right on top of each other, only an infinitesimal separation between them. And we'll do the equipotentials again first and see how that looks. And lo and behold, it doesn't hurt the circles at all to do this infinitesimalization, I guess you could call it, of the charge, or whatever the parameter is, A, that we set equal to 1 here, that is on top of it. So once again, circles everywhere on both sides of this. So this is a very analyzable geometry. It's very, well, let's just say circular. The curves here that we've got for equipotentials and for streamlines, as we'll see. We'll go ahead and put those up here as well on top of the thing. The flow lines are go now in the direction of the arrows for these things. There's a circle right there. I'll make an even smaller one, and just keep making those. And once again, you're getting a very important for later work function involving well, bispherical, a version of bispherical coordinates that's probably, well, every engineer has to learn about this, as we'll explain. These are the way you make a graph paper to do Green's functions for oscillators, which we'll study early on in Unit 4. It'll be the first topic of Unit 4. The study of resonance, oscillation with driver. And with friction. This will be one of the rare cases where we really take into account the dissipative forces, frictional forces. And the function that does that is being plotted right now in a funny kind of way, which I'll explain in a little bit here. So there you are, a bunch of circles sort of kissing each other for both the streamlines and the equipotentials. So I hold this up as something that's quite beautiful mathematically, but also artistically. So it doesn't hurt to go ahead and plot the picture of that thing. And at first it looks a little bit weird. Okay. Maybe put too much blue in there, but you can see as you look down on the thing where the pole and the hole are. Mm-hmm. We'll show some better pictures of that in a minute. They aren't quite as confusing as this one, but this gives you a pretty good idea of what it is we're dealing with here. You can sort of look down the hole mm-hmm. and poke your eye out with the pole, but there they are. And the idea is that there's something with infinite slope separating these two objects, the pole and the hole. Okay, you can see that right here there's a finite slope, but as I bring these two wires closer and closer together, we get this great big drop-off that makes it hard for you to really see the graphics. Again, better graphics needed in order to show, and I'll show a few pictures of this coming up here in the slides that have been done with the newer program of Analytic. But the basic idea is that if you start with a monopole that's A over Z, and the field that we've been studying in the last lecture and are still pictured down at the end there, and you have a monopole potential, and this is the thing that's unique about this particular field, 1 over Z, its integral, the potential is a logarithm. So this is the only power of Z, integral power of Z, that has extremely weird behavior, that is not given by an ordinary algebraic function. It's given by a logarithm. Okay, so you're seeing that logarithm and then another logarithm being put right next to it. So as we let this thing, let this del go to approach zero, we get here the fact that this dipole, the potential and the force field, is given by the derivative of the force field, in this case the force field of the monopole, and the potential is given by the derivative of the potential of the monopole, that giving us a dipole. And this process goes on, we get more and more poles. We get 2 to the n pole if we've taken the nth derivative, and I'm going to look at a few examples of that. But in any case, that is the main little thing that I want you to realize, is that eventually we'll be putting together functions to make any kind of field you want using powers of z. Okay. This is perhaps a better picture, the one that's in the text. And this is a 3D picture. If you were able to look at this, unfortunately, as I said, our system is down, our university system is down right now, so you can't look up this lecture or the text. But when you get a chance to do that, this is an easy one to make 3D, and it's quite spectacular. But you can see right here, as I go down in this pole and I circle around to the side here, there's a line of infinite slope where the surface is completely vertical. Okay.
And in a line coincident with the y-axis, it's completely level there.
And yeah, right in that region, as you go back and forth on the y-axis, a bunch of lines that are nearly vertical and one that is exactly vertical in the center and is present there. Now, once again, the curvature sum of every point of this thing is 0.
That's what we need in the app. We need something, if you
Show that,
skate along and show that they don't rotate as they...
Right. The other thing we need is the one that draws lines at arbitrary distances, which I'll come to in just a minute here. Okay, so that's the basic idea of this. Go ahead and expand the dipole. You have a function here that is the scalar potential, and then you have something here that is the vector potential. This begs to be plotted because it has a simple sine and cosine structure to it. So that's something I will do here. I think for the moment I'll switch back so that I can have 2 slides from the lecture notes side by side for comparison. It takes a little bit of time to get this back. But this is the geometrical description of this thing, looked at with just a pair of equipotential circles and a pair of flux line circles. So this one pretty obviously is making a coordinate system, and that coordinate system is called a Smith chart, and we'll be using this geometry and the chart in Unit 4 when we discuss resonance. This, as I say, is a preview to Unit 4, and what we're looking at is a plot of the Green's function for a damp-driven harmonic oscillator. Okay, so there's so much of physics that starts with the spectroscopy that goes with exciting resonances. And we're talking about one resonance at some frequency, omega 0, and then a stimulus frequency, omega s, and that makes up the real imaginary parts of a function that you see here. And this is a plot of the what we call lifetime versus beat period. It's a very important plot, but it's got a name, Mr. Smith. This is a Smith plot, and there's a Smith graph paper. How many people have seen this anywhere in your studies? Has anybody ever seen this? Well, that's the problem with physics, is they don't talk about some really deep engineering that goes on. Engineers know this thing. And it used to be they have this graph paper in their drawers, and they would figure out basically wave-like Ohm's laws, impedance matching, and all that kind of stuff that happens. And we're going to talk about that in some detail when we get to Unit 4. But right now, you'll find this graph printed on computers that do spectroscopic analysis, so that you don't have to actually draw on it. The computer will draw on it in the various lines and curves that you go across a graph like that. I'll tell you a lot about the mechanics of these things. Now, this is a more modern thing. This is a TC's HTML5 program doing just the equipotential lines, and then here's one that's doing both, and here's a top view graph of those lines taken to extremes, and when the system gets working again, you can play with these using these links. So remember, this exists. We'll bring it up again when we get to Unit 4, but it's something you can do. What's the history of the curve that we're looking at? And it helps to talk about women in physics and mathematics, because finally we're getting that equalized a little bit. And here's somebody that had to fight like hell in order to get into mathematics. Her name is Witch of Agnes. And the curve, this particular curve, and I'm going to go ahead on these graphs here just to show you what it is I'm talking about. Right there, this is the 3D picture that we were looking at before, but I have sketched on that graph cross sections of that dipole function. One of them is the Witch of Agnes. That's the name of this curve. Old calculus books would have this curve in there. It's a very simple function, y equal b over x squared plus b squared. B is a constant, okay? And it makes the witch's hat. You see, we're getting close to Halloween, right? So that's the real witch's hat, okay? They didn't come to a point like they do in cartoons. They have a nice little curve at the top, okay? So here's the Witch of Agnes, and whether she ever went and did the other side of her hat, which is this thing, that's kind of the derivative of this one, okay? And that's the thing that's true about these impedance functions, but they are just a line that's been drawn at a constant y. That's the derivative of the witch, but the actual witch is what you get if you put a plane and draw the top cutting point on the top of the surface here. Okay? So this particular curve right here has a very important maximum, and that's where the resonance is occurring. That is where the maximum response of an oscillator is, and but it's part of a function that doesn't ever have a maximum or a minimum. This is an analytic function, and it cannot have a finite maximum or a finite minimum. I've already talked to you about that, but that's part of it being analytic, okay? So this is a point, every point on there, right to there, that's definitely got negative curvature, but just as much positive curvature is had perpendicular to that thing. And the same thing is true for every point on here. There's a maximum there, but that is counteracted by an opposite curvature at that point going the other way. So the rule of the what they call average curvature or sum curvature is zero everywhere on an analytic function. This is no exception. I did not mention that the product of the principal curvatures is called the Gaussian curvature, and that is not zero, but the sum is. Okay? And just some little points of contact with this crazy stuff. Okay, there's another picture of what we're talking about here. Now, this goes on. This goes to the next step here. And you see the idea of this is every time you have a structure of some end pole, okay, starting with the monopole, you put a copy of that monopole next to it to make the dipole, but then you get that distance between them down to an infinitesimal, okay? You are doing a derivative. So this process of converting to higher and higher monopoles by taking, or end poles, by taking a derivative is very much a part of our physics. This is kind of the way we do business with the universe, is thinking about multiple functions in various atomic and molecular and solid state settings. So it really is worthwhile spending time on this simple stuff, this easy stuff that you get when you have 2 dimensions. You're using complex variable to do all of your work for you. As you go to higher dimensions, well, that's a whole nother ball game, but then this gets you started, this business here. So the next step here, and it's getting to be sort of a mess, because what I've done here is I've taken a derivative of the dipole force field, and I've gotten the quadrupole force field. At least I will get it. It's just a symbolic one right now. And the potential of the quadrupole is gotten by taking that derivative of the dipole. So that is what we're talking about here. So and you see the idea is that each time you do another derivative, you up the power, the exponent of 2. So this quadrupole is 2 to the 2. The dipole is just 2 to the first power, and the monopole is 2 to the 0th power. So here next, after this would come the octupole, the 8-pole, or whatever you call it. I guess the pole dancer is next, but not really. This just keeps going up on an exponential scale. So this is a picture here, a top view right here, and now we've got a quadrupole, and then minus a quadrupole putting right next to it results in, and these are not circles anymore, they're getting squished. So as you go to higher and higher multiples, now you're going to get more and more lobes. Here we're getting 4, next stop is 8, and so forth, and 16. Things are rapidly getting out of control here in the pole business. So that's something I think that's pretty important. Now the next thing that I would like to talk about, and this is stuff that is a little bit geeky. I mean, the whole idea of making an arbitrary force field out of all of the multipoles. Certain amounts of them. We have coefficients here. Most of the time we only have a few coefficients that are not zero. But we imagine an infinite series in both directions. Positive direction, that's a good old Maclaurin series. And of course this can be around any point. We're taking it around the origin. Here we're taking it around the origin. Here these things are actually having their sources in our laboratory. But when we talked about the force field, the first one we did here for this whole complex analysis was f of z equal z, just with a coefficient 1, okay? And we mentioned that that was a quadrupole field, but the source of it was at infinity. The quadrupole that actually made it was at infinity. That's kind of a weird idea, the whole idea of the source at infinity. Okay, so I look off in this direction, I say, well, the source is at infinity there, but the truth is it's at infinity in all directions. There's no one direction that source is sitting at. So we've got to figure out some geometry somehow to take account of that. How do you think about something with all these funny little charges, 2 or 4 or 16 or however many, charges at some point very far away, namely infinity. Where the hell is infinity? Okay, that's kind of the thing that makes this whole business sound like a fairy tale, and we need something to at least make some sense out of that. So that's what we're setting up to do here, and this is where we're also introducing the concepts that go with just the inverse map, the basic, as I say, the weirdest of these functions, these force functions, is z to the -1 power. Okay, so here is the polynomial that's going to make our field, our force field, or whatever we want to call it, the F field. Okay, and then we've got the integral of the F field. That's the potential field, and this is the only one, the one in red here, that isn't giving us a power. It's giving us a logarithm. So this one goes 0 power of z, and then right here, z to the -1, -2, -3. Okay, these are things that we have given the name 2 to the n pole, but that's a pole that's located at our home base, origin. These guys all down here are due to some sort of source located very far away, and we say z infinity. Well, where the heck is that? How do we make a geometrical picture of something as weird as that? And particularly the logarithm, as I've pointed out, is the one that's making those flowers, okay, those logarithmic curves that blossom out into the monopole, but then all of these other guys they're beautiful too. So we really need to understand that a little better. So, as I say here, all these terms, except this one pole, the monopole, have a potential term of a 2 to the m pole. Okay. And they're located at z equals 0 for m less than 0, at z equals infinity for m greater than 0. So this is just expressing the potential part of the field in honest terms. And adding a constant to a potential doesn't change it, so there is no constant term here, but there is one for the force field. Okay, and that's important, is the thing. But that has become a dipole, you see. All right, let's go one step further on this little discussion of our things, because what I can do is I can say, well, if I'm going to work with things that are infinity, maybe I could get there by simply defining a new variable, w, the inverse complex variable, and look at all of the power functions, including the logarithm of w. Okay, that's the trick. That's the trick to get some sort of geometry going here, to get a connection. So when I say AO of W, which is 1 over Z, what I really mean is, in terms of Z, I mean AO times Z minus 1. Okay, and then minus 2, well, that's associated with W to the square. So I'm working with a complex variable W. I'm going to be at infinity with my friends here that were giving me fits, trying to explain how a quadrupole field could be sourced. I'm going to go to the source now, at least algebraically. But what we need is a geometry of that. This is the geometry of the inverse map. And I think this is really cool. I think this is something every physicist should, not just engineers and not just mathematicians, but physicists need to see this. This is a way to get there. Here's the plane that we live on, higher plane. Let's think of us as the higher plane. This is the z plane, okay? There's x plus I, y, all of the possible things happening. And that's what we started with. We started with our quadrupole field. F of z gave us what we called the quadrupole field, but it was made by something that was on this plane, located, well, very far away. And the idea is using this Thales construction, I'm talking about something in 600 BC, the rectangle inscribed in a circle, okay, and that is the geometry of what we call stereographic projection from local, our home, to the infinity. So as I go out farther and farther and farther with my z, I start swinging down further and further. I bring the W point closer and closer. So I start out, say, with the z that's just very near this pole right here, and that's going to project to something that's way down to the end of the blackboard there. You only have a 1/4 inch up here. And then as I bring this one in, bring this one out, that one goes in. So this angle theta is sort of determining, how far you are. And we're talking about this absolute z being tangent theta over 2. This is a half angle right there that makes that possible, makes this whole this construction here possible. So basically what we started with as a non-trivial example in this class was, well, we showed a constant field, but the quadratic field at, near the South Pole would correspond to a quadrupole centered at the North Pole. Okay, so there's something that has a f of w equal w. That would be our thing we started with. That would be the thing that had the hyperbolas making equipotential and streamlines, and we said that is a quadrupole field, but it's been sourced by this. There's the quadrupole that actually did it, z to the -2. And so forth. This one's really easy. If we were looking at f of w equal constant, okay, so we're just talking about something that where all the arrows point in one direction. It's just a uniform wind blowing there, but that's made by a dipole at the North Pole, and so forth. You can make a connection between each of these and something that's up here. Monopole. If you have a monopole at the South Pole that's got a negative sign, you have a positive monopole at the North Pole. So it's kind of fun to make little pictures like this to show how you relate a field that's local to a source that's in infinity. Okay? Not okay. This is crazy, isn't it? But it's beautiful. It's really a beautiful piece of really ancient geometry and modern mathematics. Modern in the sense of stuff that came around 1800s. Okay, I think we're making progress here today. Now, the algebra and calculus of this is a whole nother story, which we won't tell much of here today, but I can sketch it for you. And the idea is that only this one has an integral. All of these other fields, all of these other crazy fields that we've been making here, and I go back and see, I think I'll keep this one here, and I'll go back on this one to typical field. Any of these fields that we've been talking about, besides the dipole field, if I do a contour integral, that is, figure out how much work it takes to go, say, around a loop, the only potential, I should say, the only force field that gives me a non-zero integral is this one, the monopole. It's the only one. That's because it's got a potential that's a logarithm. So you got to see that in quadrupole. I can go anywhere on that quadrupole field, draw a loop, and it's going to be zero work for me to go completely around that work. I may do some work here, but I'll get it back. So it'll be zero work to go around any loop on that in that field. Okay, and that includes one that surrounds the origin. But if you go even further back on this, look at a dipole field, or let's go really far back, and look at the monopole field, those are good examples right there. Okay, it's very obvious that for this particular one that as I go around this thing, I'm going to lose energy and lose it some more. I'm going to be getting a positive integral. Now we're getting into the argument, do I use the physicist's definition of force or a mathematician's? But in any case, the loop integral for this one just gets bigger and bigger and bigger each time I go around a loop. So this is the one that has the helical staircase that keeps changing either down or up, depending on which direction you go. And this is the only power of z that does that. 1 over z for the force. So the potential is a logarithm, which never stops getting bigger or smaller as you go around. So that integral right there is called the residue of a function, and the only function that has a residue is this crazy one, the monopole. And the loop integral of any function will simply give you the coefficient of whatever monopole exists in the power law expansion of that function. So this a minus 1 is a key quantity to start us off here. But then what we can do is we can simply multiply our function by a power of z. First z to the zeroth, but here's z to the first power. Here's z to the negative 1, and here's z to the negative 2, multiplying an arbitrary function, whatever it is. And what I'm trying to do is pull off the coefficients of the power series that defines that function. So we started with power series, now we're going to be ending with power series, but it's an enormous power series that varies. So a power series that is twice as long as most people are used to. Okay? We're never talking about stuff like that. Usually now we are. So that is the basic idea of the physics behind this mathematics, this wonderful mathematics. Now the whole idea is that these loop integrals, okay, this particular one here, we're talking about a function of 1 over z minus a constant. So now my monopole, if there was one, is perhaps located at a point that's not the origin, but some other point in the complex plane. And the idea is that for any loop around a point, this function is just exactly the value of the function on a tiny circle around the point A. Let's assume any tiny circle around Z. It can be a ragged thing, it doesn't matter. It's independent, since if there are no other poles in the neighborhood, this is an exact expression. So any contour, and this is getting funny here, that doesn't touch A, it gives the same answer. So we just write it as a general contour that's surrounding that singularity and not any other. So that's an important thing, and that is a very famous piece of calculus. The getting of a function at the value A from an integral of the function multiplied by a monopole that has its singularity at an arbitrary point now, not just the origin. Okay, so that can be repeated so that you produce. Now what happens for a positive powers here, that is for positive derivatives, and I'm talking about first a quadrupole and then an octupole and hexadecapole, 16 lobes, Each one of these gives a derivative. And at this point, if that was all we were interested in, we'd have the positive power series. So for positive powers, this is just the good old-fashioned Taylor series or Maclaurin series. Taylor if your A is not equal to 0. But we've also got n equal minus infinity, and for that, this expression has to be used. Negative derivative, what the heck is that? We don't know. But this is an integral that gives that for positive n, and then it gives you the answer you want, the coefficient of the series in the negative region. Okay, where your sources, your z's, are located in finite regions in the z-plane. Okay, so that's the basic idea of the power series having a physical interpretation and a geometrical one as well. Okay, now the rest of this is a little bit crazy, but I would like to take this one just as a, take a close look at this. This is just the Riemann-Koshi relations once again, here talking about the scalar potential, or the real part of a complex potential, and then the vector potential, or the imaginary part of a complex potential, and writing their partial derivatives out to compare them. And the idea of an analytic function is it satisfies these Riemann-Koshi relations of analyticity. And the whole idea of this is to, this time, do a mapping between, say, x and y, and then maybe we want to go to the W space at infinity, but I'm just imagining here any other complex space with real and imaginary parts u and v. I'm demanding that the W be 1 over z. It could be any function of z. But the basic idea will be that there is a mapping between these two. Now that's one of the things that this program does, and we're also trying to get this put into the new program. So I'm going to switch back just for a moment here to an example of doing a mapping. And this particular program that we've just been looking at does a mapping simply by clicking on this thing right here. Map using a potential. Okay, now real quick, I'm going to take a very simple f of z. That's f of z equal a constant. I'm going to erase all the crazy lines that I've drawn there and just look at a force field that is constant. Okay, now you might wonder, well, we started with this one, f of z equal az, and we got something pretty complicated with z squared, gave all those hyperbolas. It was a quadrupole at infinity that we were looking at the field from such a source. Okay, well, this one is a dipole at infinity, and it's just giving us a constant thing. Let's take a look at it. Okay, there's the constant. All right. Well, it's a constant for a particular value of the constant a, which I have set equal to 1. But we might as well try putting a little bit of imaginary part into that. So I'll go ahead and stick that on here. I think I can get this thing to move a little bit. Let's put a half or something like that in the imaginary part of the constant f of z equal to a. Now what does that do? Let's plot it. Okay, it's imaginary, and I take a complex conjugate of that to see what the field is. The field is down. I rotated it clockwise, which is a left-handed negative rotation. Okay, and if we're interested in the coordinates that go with that, of course, we can plot them. We'll plot the A lines for that first, just for the sake of argument. Okay, these are the vector potential lines, the flow lines, right? And I'm just being real sloppy here, but if I were to do it uniformly, you can see what I'm producing. I am producing a coordinate system that's known and loved by everybody. That is a Cartesian coordinate system. So if I'd been careful, I would have made nice graph paper. As it is, I'm not being spaced out evenly here, so I'm getting sort of a ragged but very clearly Cartesian coordinate system. Okay. Now, what you can do with any scalar, any potential field, the potential field you see is defining the coordinate system, and that's why we use the potential field to do a mapping. And what I'm going to show here, I think, I'm just going to go ahead and plot this thing real quickly if I can, using phi is equal AZ. There's what you get. And it shows the lines that I drew on that particular coordinate system, and then here's the mapping of that. Now the mapping goes the other way because I didn't have phi star, I have psi, but you see all of the things that happened right here. You see, you know, I can go here and you know, draw a picture of somebody. You know, I could draw a picture of President Trump right here and make him look angry, which he is very much these days, okay? And you can see Mr. Trump over there, and he's just been rotated a little bit. There's not much damage to him by this particular function, right? But, you know, this is what we're doing when we say, and we've already talked about a funny kind of mapping that used contact curves and all that, the action mapping. That's not what this is. This is much simpler. Okay, I pick a complex variable there, and then I find out where it winds up over here by just simply working this out. This is the simplest non-trivial example of that. Okay, and there's a Jacobian for this map from du dv to dx dy. Actually, you might call that the Jacobian. The way we did things over there was, if x was in the numerator, we called it the Jacobian. If x was in the denominator, we did the other. This particular thing is analogous to what gets our classical mechanics started. And the complex derivative looks like that. That's the dw dz, you see, all written out. And you see the partial u with respect to x, the partial v with respect to y, and then you see it flipped with a minus sign right there. You know, it's the kind of thing we've been doing all along here. But it's all based on this basic differential of du dv related to dx dy, which is this Jacobian. And the Jacobian would be the inverse of that. And that's, of course, possible. There could be a mapping z of w coming back home. And that's all pretty cool. But what I wanted to show you is, let's take a next step up. Let's pick something just one step above that, and this is part of your homework this week. I'm going to go ahead and erase the lines that I made there. I'm going to take this guy, which we know and love. That's the f of z equals z. And you remember what happened there. And it's a little bit different now because I have changed the constant here. The constant that sits right here in front of z. It's not 1 anymore. It's 1 plus 0.5. Let's go ahead and use it without erasing that. I'll go ahead here and make the hyperbolas that we know and love for a field that has, there's one that's really sharp, so these are all just hyperbolas, and you can see from the hyperbolas just that they're tipped a little bit, they're tipped down. This thing has had a new constant put on so that the axes of this have all changed to a new place. And of course the streamlines that go with this are also hyperbolas, as you remember, but now they're tipped so that they match the rotation of this coordinate system that has been done by a complex number. Remember I told you complex numbers are operators, or rotation operators. That was something we mentioned early on in the introduction of this. So let's use this function, it's z squared now, to map with this. And all of these lines will go along with it. It'll be kind of a mess, but there it is. Okay? Now, what you've seen there is kind of messed up right there. It's kind of like it's curling around in that region. That's because of the complex coefficient. Here's the set of curves that we made on our graph paper that was nicely aligned. After we've done the mapping with this thing, it's kind of a quadratic mapping, so it is made something that's pretty complicated. Let's simplify that. By getting rid of the imaginary part now, make this back to being just plain old 1 plus I times 0, and I'll say erase all those lines and make the change. And this time what I'm going to do is, without drawing anything on the coordinate system, I'll simply do the mapping. And you should recognize that as parabolic coordinates. And that's one of the things that you'll be doing in the homework, is analyzing the covariant and contravariant vectors associated with that particular OCC, orthogonal curvilinear coordinate system. In any case, that is, I think, all I'm going to say at this point. But you see, the same thing is true here. Anything that I draw, on this side, should show up. Even Mr. Trump should show up being mapped over to, well, some people would like to map him into jail, but there you see a much larger and more Halloween-looking face compared to that one. Okay, so this whole idea of doing a mapping is something that you can get familiarity with using some sort of program. There are programs around now that do something like that. With, I think, one of the students, he's not here today, pointed one geometrical program out that does that sort of thing. So, the whole idea of this is that you get, actually, another point of this is that you get a Jacobian determinant that's very simple. It's simply the derivative absolute value, dw dz squared, is that. So that's just representing the volume change or area change that's occurring. You see, we've got this considerable derivative here because we got a bigger Mr. Trump than we started with in the original Cartesian coordinate system. Okay, differential is simply going to be some scale factor times the rotation at each vector, but as you go to the next one, it would be a different value for that, because they're all functions of the complex variable, independent variables. Okay. All right. That's what we're showing right here. And what I'm asking you to do is go ahead and figure out what those covariant and contravariant vectors are for this particular coordinate system. Get familiar with that. Here's another one that I'm asking you to look at. This is square root of the variable, okay? And it gives very nice hyperbolic OCC, although it kind of messes up on the negative side because the square root becomes imaginary, but it certainly does a fine job in the positive half plane of the XY coordinates. So that is now the rest of this is just, we've only got a few minutes here, and I don't want to make you go to sleep. This is something that's kind of a hobby, but it's a hobby of every mathematical physicist that's studied the whole idea of, shall we say, different kinds of vector fields. Transverse vector fields versus longitudinal vector fields. What we're going to do here is do non-analytic functions. There'll be a non-analytic potential that consists of something that's scalar-like and then something that's vector-like. But we're not going to require it to satisfy Riemann Koshi at all. When we take a derivative of this guy, we're not going to get the same thing as when we take the curl of that guy. So this is going to be, quite a bit more complicated because now everything that we're talking about here, potential, force field, and source, not going to be a non-zero source now everywhere, is, you see it, there'll be a longitudinal scalar-like source, and there'll be a current-like flowing source possible. And here, sources, and most of the field, most of the coordinate system is zero. So this is, I didn't even think it was possible, but here's the basic idea is that we take a derivative with respect to z here, and remember that definition still holds, we're going to have a divergence of f and a curl of f, and they're not going to be equal. Now we're playing real field theory, okay? So we'll look at both the complex f and the real f, that is the f without conjugate, the conjugated f, and these two will be of interest. Once again, whatever you're doing here, that if it's the original f, then I want to do the derivative with respect to z star. That's kind of the way we started. But also, if it's f star, I want to do it with respect to z. But remember, that would have given us 0. Well, it doesn't anymore. There's going to be the conjugate source. Okay. So anyway, to make it's a little bit of a long story, shorter, we go ahead and we write out all of the parts of, say, this particular derivative, and then collect them so that this particular combination gives me that divergence of f star, the vector f star that goes to this, and this part right here gives me the curl. Again, it's just a number as a function. It's a function representing the component of curl that is perpendicular to the complex plane, if you're thinking the way you would normally for a curl. That was true before as well. So we're going to be having non-zero values for those. Before we had them all divergence and curl free. Now there's some density there making a divergence everywhere, perhaps. And same thing here, there's something there that's making a curl everywhere, some kind of current's making a curl everywhere. And that is what we have to fight with now in this thing. So I'll be showing an example of this. This is for source-free in analytic functions, these two fields, these two, remember, were the same. And we had a half of one and a half of the other, right? Put the 2 up here so we don't have that half anymore, and we can do business this way. So we're going to have a longitudinal field, transverse field. One of them given by a gradient and the other one given by a curl. That's really what it boils down to. So all possible vector fields have to be, two-dimensional vector fields have to be combinations of this. And I've got a gnarly example that's not much more complicated than what we talked about. It's an f of z quadratic one that we'll use as an example. But here's the thing I'd like it to make between the study of fields, classical fields, and the equations that we do in this class. Newton's equations, really. Everything that we've done so far is rewriting Newton's equations in fancy ways that can take care of curvilinear coordinates. Here we're doing it again, but it's kind of weird. Basically, the idea is the usual calculus. This is the calculus of fields. This is the calculus of just ordinary variables. You know, derivative of velocity with respect to time gives you acceleration. Okay, and then if you integrate that, acceleration, you get velocity. And it's all part of your freshman and sophomore physics. Okay, and then here, the integral. This is the x is the integral of v. Okay, so that's the way you go from the v to position. Just as this is the way you go from acceleration to velocity. That's an integral work there. But the derivative, of course, the opposite of that. Is taking the, getting the velocity by taking the derivative of position. Then you got double derivatives to connect these two. And I didn't bother to write two integrals there, but certainly that thing holds. Okay, well that's all we need. There is the sort of generalized Poisson equation that's taking you from the source, or taking you from the potential to the source. Now you'd like to go the other way, wouldn't you? Okay, you'd like to be able to take the source and get the field, and then finally the potential. Okay, this is kind of both headed this way, but this guy right here and this guy can go back and forth here, and you can go back and forth here. So here's an analogy of the calculus that goes with fields, attempting to make it like what you have for what we're doing in this class is velocity, position, and acceleration of lots of variables, usually. Well, here we're doing fields, which is two variables, essentially. So, I'm taking here an example. This is an actual numerical example. I've got a density of 4x, and I've got a current density of minus 4y. Just I took that out of a hat. And as a result of that, I get a, here, a source, that's what, if I give the source 4x plus I4y, that's what I get for those values. And then here, if I integrate this thing, this is the potential I get. I've got a scalar potential looks like that, a vector potential looks like that. Okay, so what will we get? We get a longitudinal field very different from the transverse field. And there are the actual equations for the thing. The now this is important. When you get this guy, has no curl. And when you get this guy, has no divergence. So this one's got lots of curl but no divergence. This one's got lots of divergence but no curl. So we break the field that we have here, which is this one. It's not too different from the one we had for fz squared, but a little sign error there, sign that it didn't have. And so here is the curl is 4y and the divergence is 4x. Okay, that's our density of charge and density of current. Okay, and this is a picture of the thing. Okay, it's gnarly. And this isn't too different from what you get if you just took f of z squared, f equal z squared. Except that f of z squared, the way we did it, was completely divergence and curl free. This has got divergence and curl all over the place. And you can see it when you put the two together. Here's a scalar potential and field that goes with that, which is a gradient. That's the longitudinal field. Here's a transverse field. And it's when those two guys get on top of each other that this goes crazy. Okay? So there's the actual field analyzed. And that's just taking for the few points that have the arrows located on it. Okay, there's the whole thing right there. And that's it for today, folks. But you may be interested in something that you may find useful in looking at something that's flowing in a two-dimensional solid lattice of some kind. Who knows? The more crazy tricks that you can put in your toolbox, the better chance you have of making some discovery at some point. So that's why I'm hoping I'm not wasting your time with things like this. I think they are potentially useful. Okay? I usually say any questions, but I know this is a silent class, but you're welcome to ask them at any time. And remember, well, that's one way to slow it down, right? So if I'm going too fast, it's your fault. Okay. Well, we'll be starting the real mechanics. The real mechanics class begins next Wednesday. Taken us a while, hasn't it?
Oh, the class within a class.
Yes.
Half of the semester.